Okay, this video is going to talk you through how to perform calculations using the CO2 equation of state. And in order to get this notebook and the associated spreadsheets, I recommend you watch the introductory video about downloading this stuff from Read the Docs. So what we're going to do is just to clear everything, we're going to restart our kernel and clear all output so that we see stuff as it appears. If you haven't installed DiadFit, again, watch that introductory video, you'll have to do that. And then you're going to load in your necessary Python packages. And you're going to make sure that this is at least 0.56 or a higher number. So there are three things that go into the CO2 equation of state. You have the temperature, the density, and the pressure. If you know two of those variables, you can calculate the third one. So we have three functions for doing those inversions. So the first function calculates pressure if you know CO2 density and temperature. And you can do that using either the Span and Wanger equation of state from 1996 or the Sterner and Pitzer equation of state from 1994. Similarly, if you know pressure and temperature, you can calculate CO2 density. So say you know a volcanic system, you think you know how deep the magma is stored, you think you know the temperature, you can work out what kind of densities you might expect your fluid inclusions to have. And then finally, if you know the CO2 density and the pressure, you can work out the temperature. These functions can also be used to help with microthermometry. So microthermometry works for the fact you're moving along the liquid-vapor phase boundary and that you basically leave that phase boundary. So that's when you have a liquid and a vapor, so a bubble, and it disappears and you come off, or when you end up with just a gaseous phase. And the point at which you move off that boundary, you know the temperature because that's what you've measured on your Lincoln stage or whatever. You know the pressure from the boundary, and then you can get the density. So this is how microthermometry is used to get density as another way versus, say, Raman spectroscopy. So let's first off just do a calculation for a single fluid inclusion. So let's say we measure the density by either Raman spectroscopy or microthermometry, and we think that it was trapped at 1200 Kelvin. So you really need to make sure this is in Kelvin. And we want to use the Span and Wanger equation of state. So here we just basically use this calculate P for rho T function and put in those inputs. And you can see it returns a data frame where it tells you the pressure in kilobars, the pressure in megapascals, the temperature that you entered, and the CO2 density. And if you wanted to try actually, let's do this in a separate cell. So let's duplicate this and say, okay, well, how different are the different CO2 equation of states? Let's try this for Sterner and Pitzer. So you can see all I have to do is put Sterner and Pitzer. You can see they are pretty similar. Your pressure is sort of 3 MPa difference. So this is a really, really small difference. Okay, so that's one calculation. Say you're on the Raman and you're super excited to know what depth your magma came from. Now let's imagine you have an entire spreadsheet of densities. So this could be from microthermometry, or this could be from Raman spectroscopy, whatever. So we basically have the sample name, the density, and the temperature. And you can call these column headings whatever you want. So what we're going to do is we're going to load in that data frame, and then we're going to use this calculate P for rho T function. But now, instead of putting a single temperature, we're going to take our data frame and then our column name, which is temperature in Celsius, and then add 273 Celsius to it. So this is your conversion from Celsius to Kelvin. You then put in your column for CO2 density, and you put in your column which has the sample name in. So all of the column names are put between these square brackets. So you run that, and you can see it's calculated pressures for every single row, and you could have 100, you could have 1,000, you could have 1,000,000 rows. Okay, so that's pressure. In volcanic systems, we often care about depth. And we have this function, convert pressure to depth. So what you do is you put in your pressure in kilobars, so that is this data frame, and then the column, P kilobars, and then you can either put in fixed crustal densities or you can choose a density model. So here we're going to use the density model of Ryan and Lerner. So what it does is it returns the depth in kilometers, and you can see it's returned to nan. So these are not a number. And that's because the pressure is outside the calibration range of this model. Now, I'm not going to go through all the possible examples in this video. There are going to be other videos, but at any point, if you want to know more about this function and the option, you can do help. So we do PF, and then we're going to do the name of the function. And it will tell you your parameters. So you have an option for pressure, in kilobars. You can change G if you're on another planet. And then you can either put in a crustal density in kilograms per meters cubed, or you can choose any of these available models, including a 2-step and a 3-step density model, where you choose the densities and the depth of those transitions. So lots and lots of flexibility there. Another thing we can do is we can use these functions to visualize how the equation of state behaves across a wide range of temperatures and densities. So here we are considering a range of temperatures from 0 to 2000 Kelvin, and we want 100 different temperature steps. We then obviously have to convert that to Kelvin, and then say we want to consider how sort of pressure and density and temperature relate, but we're going to choose 11 discrete densities to look at this. So 0.1, 0.2, 0.3 grams per centimeter cubed, etc. Then we're going to use a loop to fill out those variables. So what we're basically doing is we are going through each one of these discrete densities and we are performing the calculations for all of these temperatures. So I set up my loop here. In Python, you have to set up empty variables that have the right size before you fill them in a loop. So basically saying, can you calculate that using Span and Wanger? So I'm giving it the CO2 density, and the fact this is I means the first time through, it'll use the first density. Second time through this loop, it'll use the second density. And it's doing this for all of the temperatures, so all 100 temperatures. And the same for Sterner and Pitzer. That's going to run. And we can look at the outputs of this. So anytime. So you can basically see this is for each loop, you get a panda series of pressures, or after each loop, it is appending it onto this NumPy array. So we use NumPy because it's much, much faster. There's basically an XY grid of pressures for each sort of density and temperature. So what we can do is we can plot these. So again, I want to plot sort of each separate density as a separate line. So that's why I'm writing this in a loop here. And what this basically shows is that, so this line is for your 1.1 grams per centimeter cubed fluid. So you can see for a given temperature, what the pressure would be. And then all the way down to these other densities. So this is basically allowing you to sort of visualize in pressure, temperature, and density space very, very computationally quickly how the equation of state works. Now, something else we might want to do is compare the different equations of state. So that is a plot just for, if we look, we are just using the Span and Wanger equation of state. So here, and again, I'm not going to go through what every line is doing, but you know it's an option, and you could use ChatGPT to ask what each of these lines of code is doing. But basically, here we're showing what the Sterner and Pitzer equation of state looks like. Here we're showing the same plot for Span and Wanger, and you can see the lines are here, so for what densities they represent. And then we're going to plot the two of them together on top of one another. So you can see they really only start to diverge at about 1,200 Kelvin. And even then, this is a relatively small difference. Okay, so that shows the power of these functions to perform thousands and thousands of calculations to visualize these equations of state. Let's say that we want to calculate density for a given pressure and temperature. So this could be you have a ramen, you want to know how much you want to calibrate it, you know approximately your volcanic systems, pressure and temperature. Let's work it out. So say we think our magma is stored at a kilobar and 1400 Kelvin. We could run this, and that means we would be expecting a fluid with 0.3 grams per centimeter cubed. Again, we can do all sorts of visualization. So here we're using pressures between 0.01 and 10 kilobars with 50 steps in between. And we're going to perform the calculations for 1400 and 1200 Kelvin. And then we're going to plot them. So this allows you to show for pressure on the x-axis and density on the y-axis, sort of, you know, how pressure relates to density, but also how temperature sensitive this is. So you can see going between 1200 and 1400 Kelvin, if you have a set density, it doesn't change your pressure by an enormous amount, like considering that's quite a large temperature uncertainty. Over here on the right, we're actually plotting for each of the temperatures what the density using Span and Wanger versus the density minus Sterner and Pitzer is against pressure. So you can see these equation states are really similar. Like this is smaller than the uncertainty of your Raman spectrometer. So really the choice of equation of state does not matter that much. Okay, the third calculation is, say you know CO2 density and you know pressure, you can calculate temperature. So at 0.3 grams per centimeter cubed and at a pressure of 1 kilobar, you can see you have 1,403. Obviously, some of this inversion, there are rounding errors because we are iteratively converging, so just be aware of that. And then Sterner and Pitzer, you get a slightly different temperature. Okay, what else can you use these calculations for? Well, we can use this microthermometry function I've written. So it calculates the CO2 density for a homogenization temperature. And this is really useful because quite often Raman measurements are done at room temperature. And for certain CO2 densities at room temperature, you will actually have a coexisting liquid and vapor phase. And you might want to know, what are the densities of those phases? Because if you're analysing at room temperature on your Raman, you will have those two coexisting phases. And unless you are laser heating, and there's a great paper by Charlotte DeVitri coming out about that soon, it's not really thermodynamically possible to have densities between those. So let's consider temperatures between 17 and 25 Celsius. This is pretty typical room temperature. And we're using the Span and Wanger 96 equation of state. That's the only one we actually have for this function. Most papers use that. So that's what you have to use for this. So you can see for this temperature, these are kind of the coexisting liquid and gas densities. So we can plot those up. So you can see at 18 Celsius, your bubble, which is two-phase, will have a liquid density of about 0.795, and it will have a gas density of about 0.172. So you can use this, if you know the temperature of your lab, to be kind of what the range of densities should be on your Raman outside of error. Okay, let's say you're doing microthermometry instead of Raman spectroscopy. Let's say that we have measured the homogenization temperature of a fluid inclusion to be minus 18 Celsius. We can say what sample this is in case we want to append these later into a data frame. And then we want to say, did it homogenize to a liquid or a vapor? And then finally, again, the equation of state, but Span and Wanger is the only option at the moment for this function. So you can see that it tells you the density of the liquid and the gas at that point on the phase diagram. It tells you what you entered for your homogenization temperature. It tells you what you entered it homogenized to, and it tells you your sample. And crucially, it tells you the bulk density. So because you said this homogenized to a liquid, its density was 1.02. If instead we replace that with vapor, you can see your fluid inclusion density would be 0.05. Okay, so again, useful to have a single one when you're sat on Lincoln, but you could also load in an Excel spreadsheet. So again, this is linked at the top, so you can download it from GitHub. But say we have a set of homogenization temperatures we've measured, some sample names, and a letter code of whether it homogenized to liquid or vapor. So we can load that in here using the pandas read function. And then we are simply going to enter into the function the name of this data frame and the column heading, sample ID, column heading, and what it homogenized to. So you could call these columns whatever you want, as long as you put the column names here. As you can see, here are your bulk densities from all of your measurements. So this is extremely fast. Now, when we do microthermometry, it is hard to spot the phase transition, and we might want to propagate the uncertainty in that. So we can do that using this function, propagate microthermometry uncertainty. So say we measure a homogenization temperature of minus 30 Celsius. So say we think that the 1 sigma error on that is really 0.3 Celsius. Say we've measured 5 or 10 of those and we've calculated the standard deviation, and that's what it is. We can say how many duplicates we want for our simulation. So you could set this as 100 or 1,000. It's just going to smooth out the results. Again, specify your equation of state and what it homogenized to. And then finally, you have to say, do you want normal or uniformly distributed error? So here we're going for normal, and this was an absolute error. You could also enter a percent error and then put percent here. So what this returns is it returns the average. So for all of those 100 simulations, it returns the mean density of the gas at that point on the phase diagram, the standard deviation of the gas, the mean density of the liquid, and the standard deviation of the liquid, as well as the error in temperature that you entered. And then it also returns a data frame for every single simulation. So in this particular instance, this will be 100 rows long. So we can plot this up. So we can say, okay, well, what did the distribution of temperatures that we put in look like? You can see it looked like this. And then how does this correspond to variations in liquid and gas density? You can see, okay, so that was for 100 simulations. What if we change this to 1,000? You're basically going to get smoother and smoother distributions. It's a playoff between a smaller number of simulations is faster, and the more simulations you get, the closer you approximate that normal distribution. In terms of propagating uncertainty and other equation of state calculations specifically for fluid inclusions, that is going to be addressed in a later video, so please watch for that.